Good morning. Welcome to the first part of Unit 11. In this part, we are going to look more specifically at conservation of energy. And for conservation of energy, we're going to begin by reviewing conservative forces and non-conservative forces. We saw last unit that conservative forces do not depend on path. It's things like gravity, the force due to a spring. Non-conservative forces do depend on path, so friction and tension. And I made the distinction to remember that no matter which way you move, gravity always points downward. But friction follows your direction. It follows whether or not you're on a slope. It changes direction depending on what is happening as you move. So conservative versus non-conservative forces. Conservation of energy states that given only conservative forces acting on an object, energy can change form from one type to another, but it cannot be created or destroyed. So what this is saying is essentially, if I only have conservative forces, then when I think about the work energy theorem, that's a D, equals change in energy. If I only have conservative forces, then there's no force that I can plug in here to do work. Oh, yes. So that means that our change in energy is going to be 0 joules. So whatever I had to begin with in total has to be what I had at the end in total. Okay, so remember our three types of energy: kinetic energy, elastic potential energy, gravitational potential energy, that we met last unit. Remember also there are other forms of energy: nuclear, solar, thermal. But typically when we're dealing with conservation of energy, what we're really after is the mechanical energies, which are the three that are listed at the top. So let's give an example of dropping a ball. So if I give a ball 100 joules of gravitational potential energy by lifting it upward, what is its kinetic energy when, and then I give you a list of gravitational potential energies. The idea to this example is that this is my total energy. And at any point in the ball's motion, the total energy is equal to the GPE at that point plus the kinetic energy at that point. So if the GPE is 75 joules and my total is 100, that means that the kinetic energy has to be 25 joules. If GPE is 50, then kinetic has to be 50. If GPE is 25, the kinetic has to be 75. And if I have no GPE left at all, then kinetic has to be 100. And in each of the four cases, my GPE and my KE add up to my total energy of 100 joules. Okay. So now let's think of a mass on a spring. We're going to pull the mass back and release it, and we want to think about what's going on with the kinetic energy and the potential energy as it oscillates. For this, I like to draw a series of pictures. Ideally, they'd all be overlapped, but then you can't really see what is going on. So instead, I'm going to draw a series of about 5 pictures. So the first here is the mass when the spring is pulled out, and if you want to imagine a surface for it to oscillate on so it can do left, right, that's fine. And then it's released. But at this moment, it's pulled out and it's held. So the velocity equals 0. It's released, so the mass starts moving this way. At some point, it hits the equilibrium point, which means it is still moving that way, but it is now moving as fast as it can. And then it continues moving this way because it was moving at its equilibrium point, so it overshoots, if you will. But at some point that spring is compressed as far as it can be and it stops. And then after this point, the block turns around and starts oscillating back outward. So where is the potential energy the greatest? Potential energy is going to be the greatest wherever the kinetic energy is the least, which is at either endpoint because it's not moving. Where is kinetic energy the greatest? Kinetic energy is the greatest where the elastic potential energy is the least, which is by definition equilibrium. So here EPE equals 0, and here kinetic energy is as big as it possibly can be. That's also signified by the fact that I told you at this point that the velocity was maximum at the middle of oscillation. In the middle, two spots, you have both EPE and KE, but neither is as big as it can be or as small as it can be. Next, let's consider two kids on a slide. So you can see we have kid A and kid B. They both start this from rest at the top, and you can see the height of the slides are the same. So the question is, which kid is moving quickest at the bottom, giving them the most kinetic energy? And typically the answer I get is child A. Okay. So now let's think about this from an energy perspective. Notice the gray line in the background telling us that these slides are at the same height. So whatever GPE kid A has, kid B has the same GPE. So GPE A has to equal GPE B because they're at the same height. Okay. Which means, by conservation of energy, that the kinetic energy at the bottom has to equal the kinetic energy for B at the bottom. Conservation of energy. So let's make some notes here. This is because it's at the same height. So the GPEs are the same because it's the same height. Kinetic energies have to be the same by conservation of energy. Okay. They have the same kinetic energy at the bottom. There's a couple of assumptions that have to go into this statement. One is that we can ignore friction. That's doable. We just have to, make the slide super slippery. Completely doable. The other thing to consider is which slide is steeper. Everybody's going to say, look, A is by far steeper. I'm not going to disagree with you. 100% agree. Why does that make a difference? Kid A is going to have a steeper slide, and therefore the change from GPE to KE will happen more quickly, which is what's going to make it seem like he's moving faster. He has a greater acceleration. One more for here. So we're sitting and watching a pendulum. Okay. Conservation of energy says that that pendulum should oscillate to the same amplitude every swing, but instead you see the amplitude slowly decline. Okay, so what are we talking about here? So let's make two drawings. One is the real pendulum. And let's pretend that the real pendulum, if it were hanging straight down, would be there. And to one side it oscillates to here, and to the other side it would oscillate to there, where these are supposed to be at the same height, and roughly are to my ability to draw. And it would just swing back and forth between those two endpoints forever. Okay. Oh, I said this was the real. This is the ideal. Dreadfully sorry. Okay, now let's think about the real pendulum. Same sort of idea. You pull the real pendulum back and it lands here. I'm going to do my best to draw a line here. And it swings, but when it gets to the other side, it goes a little bit less. And then it swings, and when it comes to the other side, it again goes a little bit less, and it goes a little bit less, and a little bit less. So if I were to watch as a function of time, the amplitude of this one, so amplitude of the swing versus time, I would always hit the same amplitude, again, to within my ability to draw this thing. Okay, if I make the same observation over here, amplitude as a function of time, it starts high, it goes a little lower, a little lower, a little lower. And eventually it peters out to nothing. So where'd the energy go? Why does this thing not conserve energy? Well, remember, for the statement of conservation of energy, we had to get rid of all forces that could do work on the object. With a real pendulum, we can't get rid of those. Okay? So forces that are acting on the real pendulum that we need to consider. Primarily, they're forms of friction, but I will enumerate a couple of them. So friction at the pivot. What is this up here? Is this a string tied to the ceiling? Well, that's going to be very frictionful, if you will. Another one is air resistance. And we can do steps, we can take steps to mitigate the air resistance, but we can't remove it completely. So what can we do? Well, the real question is, what is the mass of this object versus its cross-sectional area? And if you make the mass big and the cross-sectional area small, then the air resistance goes down, right? But for a real pendulum, you cannot get rid of these frictionful forces, and therefore you have work being done, and therefore energy is not conserved. This concludes this part of Unit 11. In the next part, we are going to work mathematical examples concerning conservation of energy.